Hello everyone. In this section of the course we will be speaking about air flushing as a soil or groundwater cleanup technology. We'll first be speaking about mass transfer in this segment, and then in the following two segments we'll be speaking about soil vacuum extraction, and in the last segment we'll be speaking about in situ air sparging. So I'll frame the problem as an in situ air flushing technology in which we want to flush air as the mobile fluid through a contaminated zone, and the goal is for mass transfer to occur between the impacted zone, that would be the non-aqueous phase liquid, the dissolved phase, or the solid phase, would then have mass transfer into the mobile air phase. So the soil vacuum extraction, which takes place within the unsaturated zone, involves phase transfer, as I spoke about, and if it's pulsed, then it becomes a bioventing type of process in which perhaps ambient air is added into the source zone, the system is turned off, so it's at rest, and the oxygen within the ambient air is the electron acceptor. So this segment is about mass transfer, in which we force ambient air through the Veda zone to reduce the gas phase concentration. That way we are disturbing the equilibrium that's present. We have our mass transfer to the gas phase, and we have a reduction of the overall soil concentration. So the equation at the bottom of this slide is the total soil concentration on the left-hand side equaling the NAPL concentration, followed by the dissolved phase concentration, followed by the gas phase concentration, and then on the extreme right-hand side is the absorbed concentration. So in a soil vacuum extraction system, we want to reduce the gas phase concentration down to encourage mass transfer from the other three phases into the airstream. The process of mass transfer is obviously controlled by the contaminant itself, involves a conversion between the dissolved phase, the NAPL phase, or the solid phase into the air phase. So it involves what is called the volatilization process, where you convert from a solid or a liquid into a gas vapor state. It involves the process of evaporation and will cause a substance to become vapor phase. And then it is controlled by the vapor pressure of that particular compound. So let's begin with the mass transfer between an infinitely in size water phase and an infinitely in size gas phase. And the mass transfer across the gas phase, water phase interface is controlled by Henry's law, that is the water-gas equilibrium, and it is simply the ratio between the gas phase concentration and the aqueous phase concentration. There's a way to express that in a nice form that's called the dimensionless Henry's law constant form, that is Kh prime equaling the concentration of the gas phase divided by the concentration of the aqueous phase. And in that case, Kh prime is Kh over RT. R is clearly the ideal gas law constant, and T is the local or ambient temperature in degrees Kelvin. So let's go back to our water phase and our air phase and draw in those particular interface a stagnant tube film model. I'll start off in the well mixed water phase, where the concentration everywhere is at C sub W, that will exist to a small length away or small stagnant zone away from the interface. And at that interface, there's a concentration gradient as established between the interface and the stagnant, or the thickness of the stagnant water phase. At the actual interface, which is here, at the actual interface, the phase change will occur, and that, of course, again depends on the magnitude of the Henry's law constant. Then in the air phase, we have a diffusion profile again through the stagnant gas layer of length or thickness small z sub g, and then into the well-mixed gas phase. So again, at the equilibrium is at the gas-water interface, and again that's controlled by Henry's constant. So for this particular example, we have mass that is being moved from the aqueous phase to the gas phase. And that mass transfer then, big J, equaling a K is some mass transfer coefficient multiplied by the difference between the aqueous phase concentration and the gas phase concentration. Note that I've got them in quotes because they are not in the same phases. So we have a gas phase flux between the interface and the bulk gas phase. We have a water phase flux between the interface and the bulk water phase. And at steady state, those two fluxes are the same. So if you put them to be equal, rearrange the math with some algebraic help, perhaps a full page of algebra, you end up with an expression that is J is the mass phase flux, which is a product between a constant based on the length of the stagnant interfaces and the diffusion coefficients, multiplied by the driving force, which is the difference between the water phase concentration and the gas phase concentration scaled by the Henry's law constant. The quantity within the square brackets is also called the volatilization velocity, or VTOT, that is over here. So if diffusion within the water phase controls the process, then the volatilization velocity is approximately equal to the diffusion coefficient in the aqueous phase divided by the thickness of the stagnant aqueous phase, or converse, if the gas phase is controlling, then the volatilization velocity is controlled by the diffusion in the gas phase divided by the thickness of the gas phase stagnant layer. So that's the transfer between an aqueous phase and gas phase, some very important theoretical considerations. Now when we go to the pore scale interest, where we would have, let's say, a mobile air phase in blue here that would then pass by the grains or the advective pathway as such that it would come close to the red here is non-aqueous phase liquid in the pore space. The arrows show a diffusion pathway between the non-aqueous phase liquid within the pore space as they would then dissolve into the aqueous phase and then transport themselves through the diffusion process into a mobile pathway. And these are the two endpoints. We have one is we have blebs, or small residual on your right, and on the left we might have a saturated zone of light non-aqueous phase liquid. The interface mass transfer has been agreed to be a function of the mass transfer rate coefficient, a driving force, and the interfacial area of the non-aqueous phase liquid and the gas phase, and is expressed typically as something like this, where we have JA0 is the rate of mass exchange per unit volume of porous media. A0 is the interfacial area per unit volume of porous media. K is the specific mass transfer rate coefficient. CS star is the equivalent maximum gas phase concentration for that particular compound, and CG is the local gas phase concentration. Now, the interfacial area, very hard to quantify, and is only likely possibly to be estimated at a lab scale. Very typically, that the interfacial area becomes lumped with the mass transfer rate, and it's lumped into K0. So A0 times K becomes K0, where K0 now is the mass transfer rate coefficient. There's been extensive experimental work to calculate mass transfer rates and attempts to correlate those rates with various parameters of the system, including Reynolds number, Naple saturation, the mean or median grain size, or some other properties of the porous media, and various parameters that describe the retention, the capillary pressure saturation curve. The Sherwood number, which is defined as the ratio between the rate of mass transfer and the rate of diffusion mass transfer, has been used in these experiments. So as I said, there's been quite a few experiments that have been performed, and here is one for gas Naple concentrations, where the experimenters were able to show that the Sherwood number, this SH0 here, is a function of the Peclet number and D0, which is the ratio of some grain size parameters. So the Peclet number itself is the ratio of advective transport over diffusive transport, and in the case of gas phase, Vg is the gas phase velocity. Now, what I've shown here is just one possible correlation, and there are many, many others that exist. So that's just a glimpse into the mass transfer that's required within a treatment zone during soil vacuum extraction. In the next two segments, I'll be speaking about a case study dealing with soil vacuum extraction, and follow that with in situ air sparging. That's all for now. Hope to see you in the next segment.